All right, so the first way that we'll learn about tweening is just a basic form of tweening, is linear interpolation. Basic tweening. Linear interpolation. Now in computer graphics we have a shorthand name for linear interpolation, and we've kind of turned it into a verb. They'll say, oh, just lerp that. Lerp. It's kind of silly, but that's what people call it. You call it a lerp, or you lerp that. Linear interpolation. It's not spelled right. It's not an acronym. It's short for linear interpolation. So this is just a really, really simple method of tweening. And all that you do is you evenly space out all the pieces in the middle. Simple method of tweening where you evenly space out the in-betweens. Okay, and this is why it's called linear interpolation, because it just moves along a straight line evenly. So you can imagine we have a scene, and I have a keyframe here and a keyframe here. This is 1, this is 2. You just draw a straight line between them, and you evenly space out however many steps you have. So for example here, you might have, you might decide on 10 steps or something like that. And you determine how many steps you have, you divide up the change by the number of steps, and you evenly step along. It turns out that we've actually seen this before. Turns out that it's just like interpolating between two vectors. And where we saw this before were our parametric equations. And parametric equations is a really nice way to think about this. So I'm going to draw it out. So imagine I have a configuration A and a configuration B. And let's just use spatial position because it's the easiest to understand. If we think about it in terms of a parametric equation, then I have t is 0, I'm all at A, t of 1, I'm at B, and then along the middle you have different t values like 0.5 in the middle. And you could imagine having different t's as you go along. So in this situation then, given, I'm going to put this in green, n steps, where you determine how many steps you want to interpolate. And I'll make a side note because there's a very insidious off by 1 error that'll come up again. This gives us n by 1 in-betweens. Okay, and the reason is if I have n steps along, if it takes me n steps to get to 2, then you don't include the end point because it's a key point, a keyframe, so you get n minus 1. That'll come up later. You can debug that in your code. I just want to mention it. So given n steps, to calculate t at step I, it's really simple. T is going to be I divided by n. That's it. So for frame I, so you can imagine back in our here, you can imagine this is step I. Okay, not t position I, it's step I, and we want to find out what the t value is. So we just do that little simple ratio. And just to make sure you get it, if I is 0, then t is going to be 0 over n, which is just equal to 0, which matches the first location. If I is n, which is the last point, the last step in our equation, then t is going to be n over n, which is equal to 1, which is the last point. Now, depending where you look up, they'll have the off by 1 handled differently. I like to have n steps for n minus 1 in-betweens. Other people go, no, it's n in-betweens with n plus 1 steps, and then you divide by n plus 1. It doesn't matter where the plus 1 or the minus 1 is. It's just a ratio. It's not a big deal. So we can calculate a t evenly across as I increases, we could put this into a for loop, and now we have t values along that interpolation. Once we have the t value, we can convert that into, I'll switch to blue, we can convert that into an actual number using the linear interpolation formula we learned in the parametric equation section, which turns out to be really, really simple. It's just going to be 1 minus t times a plus t times b. Okay? So again, we can work through it. When t is 0, 1 minus t is 1. We're going to get 1a plus 0b. So we'll get a. So when t is 0, we get 100% of the a value, which is what we want. When t is 0.5, let's see, 1 minus 0.5 is 0.5. I'm going to get 0.5a plus 0.5b. So it balances them evenly. Half a, half of b. And then when t is 1, 1 minus 1 is 0. We don't get any a at all. We get b. So this very, very simple math will interpolate between point A and point B. And we can just wrap that in a function. We can say, let's return this. We'll call it a function lerp, which takes an a, b, and a t, and that's it. This is what a lerp function looks like. And maybe I'll write this out. If we move t from 0 to 1, lerp calculates the result between a and b. Okay, so that's really nice. So processing actually has a lerp function built in. But I always found that a little silly because it's so trivial to implement. I just did it, right? Trivial to implement. So I'm not sure why they would put a lerp function in. All right, so the other thing to mention here is this is actually a one-dimensional function. And what I mean by that is it's a scalar value. It only goes between a and b as a scalar value. So in 2D, what do? We just separate our dimensions and do them separately. In 2D or in 3D, I use once per dimension. So you can imagine I lerp my x, I lerp the y, I lerp the z. Separately, it'll work just fine. And the same thing goes for color. You can lerp RGB, you can use it for size, you can use it for whatever you want. Okay, so you can lerp these other parameters, anything that you want, no problem. Okay. So I'm going to do a demo here. Did I mention my earlier demo? Did I mark it? Yeah, I did. So I'm going to do a demo here, and we're going to work through that for a few minutes. Okay. So here's demo 4 that you'll see posted online. And so what happens is we have A and B. A is our starting position, X and Y, and B is the end position. Maybe I should put a comment in here, right? And then B is the end position. I've also determined how many steps I want to go in between A and B. You know, so -1 is the bottom left corner, right? 0, 0 will be the center of our screen, and I'm going to interpolate 10 steps along there. I also keep track of my current steps. Step 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10 will be the final point, so keep track of that. We'll come back to these things later. That solves the problem we're going to come up against. So I've set up my canvas, I've set up my ortho, and I'll come back to this. So when we draw, we clear, we reset our matrix. The first thing we do is we calculate our t. Current step divided by steps, it's just a ratio, that's my t. And then I call Lerp function, which I'll come to, I've implemented it myself. I call Lerp with t and the ax position and the bx position. So I'm going to calculate an x that's interpolated between a's x and b's x. Remember, a and b are my two positions, right? A is x and b x, we interpolate between them, it gives me my new x in the middle somewhere at that t. I do the same for y. I call lerp again with the same t value because we're moving along that same parametric equation, but instead of interpolating the x, now I interpolate the y for a from a to b. So as t is at 0, I get a, t at 1, I'll get b, and it'll smoothly go between the two as t increases. And then I push my matrix, and I draw my shape, which is just a quad. I've also added this code here. Maybe I shouldn't comment this. I'm going to call this debug visualization. And what that does is I want to draw the line from A to B so you can see what line I'm interpolating across as the quad moves along, okay? But we don't need to worry too much about that. It's just going to show you the line that it's interpolating across. And then once I'm done, I say, okay, step +1, and then I loop around with my mod here. And this +1 is important here. Instead of mod steps, I mod steps +1 just so I include that final keyframe. If I modded steps, t would never be 100%. So this way t goes from 0% to 100%. That's it. This is my whole function. I draw, and then I'll interpolate along along that line. Now I'll show this. I added a key press where if I push plus, I can add one more step or take away a step. So let's see what this looks like. So I remember I have this quad that's going from the bottom left corner to the center, and that green line is my debug line, and you can see it's blurring along really fastly. In fact, it might look like you see multiple squares. You don't. This is persistence of vision again, but it's moving along way too fastly. So here's the first thing that's interesting. I'm going to push plus, and I can increase how many steps, and you'll see as I increase the number of steps it takes, it slows down, which makes perfect sense because I'm drawing this at 60 frames a second. So if I'm drawing at the same speed but it takes more steps, it's going to slow down and go more smoothly. In fact, if I go to 60 steps, it should take exactly 1, 2, 3. This is like a clock. It takes 1 second to go from the beginning to the end. And as I increase those steps, it goes more slowly. So that's the first thing I want to show you. Now the second thing, so it's interpolating along, no problem. Now what I've done is I've added this mouse press code here. If I click somewhere, it changes my endpoint, my B, from center of the screen. It'll actually change that to the mouse location. And again, this funny code here, that just converts mouse from the viewport coordinates to the world coordinates, -1 to +1. So if I click somewhere, it'll interpolate to my mouse instead of center of the screen. Now what I want to highlight here is a problem with linear interpolation. Let's click over here. See how fast it's moving? The reason it's doing this is because I still have 72 steps or however many steps I have, but the distance is more. So each step, I need to move more to get there. So if I have the same number of steps, 70 steps from beginning to end, with a big distance, I must move faster. If I click down here, it moves slower because same number of steps, a smaller distance. So this is a problem with linear interpolation, is it can be tricky to get the speed right based on the distance. So let me show you how we fix that. So this is the first thing. It's pretty cool. So this is where we get into these numbers I said we'll ignore until later. What I've done is I said, well, dots per frame, this is a constant. How many dots do I want the thing to move every frame? Let's just say 1 pixel a frame. Okay, fine. And then what I do is I calculate how many dots are there per world coordinate unit. Remember, our world goes from -1 to +1, so it's a 2 by 2 box. So all I did was, on the beginning of the program, I took the biggest dimension, which in this case they're the same, divided by 2. So I have 640 divided into my 2 by 2 box. It'll tell me how many pixels I get per 1. So in this case, it'll be 320. We could have done that, but this is nicer because I can change the screen size. It'll still work. This tells me how many pixels per world unit. Now let's just go down here. I have a new function I want to show you. Oh, I didn't go over the Lerp function. Yeah, here it is. It's just like in the notes. No surprises, so no big deal. But this is the function I wanted to show you here. Calculate steps. So previously, what we did was we had our steps fixed at 10 or something, and then when I clicked the mouse, or sorry, plus or minus, I could increase or decrease steps. Instead of having a fixed number of steps, we can use our knowledge of how many pixels are on the screen to say, how many steps should I take to achieve the speed that I want of 1 dot per frame? So down here then, what I've done is we can calculate that. First, we calculate the distance between our 2 key points. a and b. And that's just ax squared minus bx squared. So ax minus bx squared plus ay minus by squared, all square root. This is a standard Euclidean distance function. So we calculate that distance, and then what we do is once we have that distance, we figure out for this many distance, how many dots per unit do I have, which will give me a number of dots, and then how many dots per frame. So you divide by that to get how many frames we should take. Okay, so this is something you could probably work through on paper if you're confused by it. But the key point here is convert from distance to number of frames at the given speed, and our speed was one dot per frame. So I can calculate how many steps. So when I click somewhere, it'll take the distance, calculate how many steps it should take to get there to move at our speed, and modify how many steps we take in our interpolation. So depending on the length of the line, it'll interpolate fewer or more steps just to keep that consistent speed. So let's look at our mouse press code here. I'm going to on-comment this. So after I click somewhere, it'll calculate steps for us. So let's start our program. It'll start with this crazy 10-step interpolation, but I'm going to click here with my mouse. And what it did was it calculated this at the bottom here. It said, hey, to get the speed we want, we should do this over 466 steps. I'm going to click up here. Look, it's moving at the exact same speed, except now it says, to do that, I want to take 893 steps to go between t of 0 and t of 1. It wants to take all those steps. If I click down here where it's really tight, oh, only 71 steps, but it's all moving at the same speed no matter where I click. Okay? No matter how long it is, it's moving at the same speed, because what I've done is I've just calculated how many steps should it take. So that increment in my linear interpolation stays the same. Really simple math, but it can be tricky to get your head around. The last thing I want to show you is just a little piece of code I built in, which is nice. So what happens now is if I click the mouse somewhere, let's take a look. It'll calculate the x and the y at the current location, fine, just like in the draw. But then what it does is it sets my starting point to be the current location of the cube, the quad. So if the quad's here, it calculates, where's the quad right now? Well, let's make that our new starting point. But let's make the mouse the new ending point. And again, we convert from screen coordinates to world coordinates. So if I click somewhere, it'll continue from where it is as a new starting point and interpolate towards the mouse. And what's really cool about this now is because I've calculated the speed to be the same, it'll keep following my mouse and doesn't change speed no matter how far I click or how close I click. Okay? It's just recalculating. The green line is showing my A's and my B. It's recalculating those points and using linear interpolation along the way. So this is really neat. Download this demo and play with it. It's really important that you understand all the pieces that are going on here. Let's go back to the iPad. Okay, so I'm just going to basically highlight this really important point by writing it out that I went through. The speed of the change. So how fast it goes between 1 and 2. This depends on the number of in-betweens. Okay, it depends on the number of in-betweens in relation to how big the change is. If I want to keep the same speed and I'm going to go double the distance, you need to double your in-betweens, right? If I want to keep the same speed, I want to half my distance, I need to half my in-betweens. And you can calculate this just using ratios and a rate of change calculation. So study the example I posted. To normalize regardless of how big or small the change is. All right, great. Okay, I'll stop it there, and we'll come back and we'll learn more about lerping.